And so yesterday, and by yesterday I mean Tuesday, obviously, was kind of all about what is an atom, how is it made, the protons, the neutrons, the electrons, what are they and how many of them are there in each different atom. So today we're going to kind of focus in specifically on the electrons themselves. Make sure it's the right. Yeah, there we go. So as always, I'm making sure to record this video just like I recorded the one talking about atomic structure last time. So the one about the electrons, I'll make sure to upload it and post it onto the Google Classroom right here shortly after class, so that at any point in the future, if you want to go back and rewatch some of the notes that we already went over together as a class, you can watch me go through and explain those in these different videos right here. So we are at the very end of week 3 here, finishing up talking about atoms and the periodic table. And like I said, today we're really going to focus on the electrons. So there are a couple kind of main topics that we're going to go over today. We're going to talk mostly about electron shells, kind of what they are and how they organize the electrons around the atom. We're going to talk a little bit about reactivity, which describes how likely certain atoms are to react and go through a chemical change with other atoms. And then at the end, we're going to talk about the difference between metals, metalloids, and nonmetals, which are 3 of the kind of different main types of atom that we find on the periodic table. But the first part, and probably the biggest or most important part that we're going to talk about today, are these electron shells. So if you remember, on Tuesday, we went over some of the major types of particles that make up an atom. We have the protons, which are the little positive charges in the nucleus right here. The neutrons, which are those little neutral charges that also float around in the nucleus right here. And then the electrons, which are outside of the nucleus. So they kind of orbit around the center of the atom. So yesterday when I was talking about the electrons, I phrased it as like, oh, we just have these electrons out here and they're kind of zooming around the nucleus, which partially is true. They are on the outside and they are in motion, but it is not completely random. It's not like all the electrons are out there and they're just kind of flying around willy-nilly. Instead, there is a very, very specific way that electrons get organized around the outside of an atom. So the way that electrons orbit is in things called orbitals, or mostly shells. So I'll be referring to electron shells a whole lot over this next set of notes. So if you imagine these shells as kind of like layers of an onion, essentially, or like the little like Russian nesting dolls, where there's a little one inside the medium one, inside the big one, inside the really big one. That's kind of the same thing with our electron shells. The nucleus of an atom, so these symbols represent the nucleus, is surrounded by kind of this layer upon layer upon layer of electron shell. And there is a specific way in which electrons get put onto these shells. So the main thing to take away from these slides right here is that the first electron shell, so the most inner layer of the shells, can only fit 2 electrons on it. So the 2 most basic elements that are out there are hydrogen and helium. Hydrogen has 1 electron. Helium has 2 electrons. So helium has the max number of electrons on that first electron shell. So first shell right in here is 2 electrons. What happens if you have more than 2 electrons, as most atoms do? What about if you're lithium, right here, and you've got 3 electrons? Well, you start off with the first shell, and you put 1 electron down, then you put 2 electrons down. But you still have 1 more electron to go. You've put down 2 out of your 3. So that third one will go on the second electron shell. So the second shell is kind of like the next most outer shell. And the second shell is a lot more spacious than the first shell. It can fit 8 electrons on that shell. So the first one can only fit 2, but the second electron shell can fit up to 8 total. So if you have an atom like carbon, carbon has 6 total electrons. So as always, we start off with the first electron shell. So I put our electron 1 and electron 2 on the first shell. And then the remaining 4 will go on the second shell. So number 3, number 4, number 5, and number 6 will go on the second shell. So carbon has a full first shell and a half full second shell. There's only 4 electrons on the second shell of carbon. If we want to look at an electron or an atom that has the first 2 set of shells completely filled up, we can look at something like neon. Neon has 10 electrons. So when neon is getting its electrons organized in its shell, we have the first 2 go on the first shell, as always, 1 and 2. After we put those 2 down, we start off with 10. So now after we take out 2, we have 8 remaining electrons. So all 8 of those can fit on the second shell. So neon has a fully filled in first and second shell. It's got 2 electrons on the first shell and 8 electrons on the second shell for 10 electrons total. But neon is not a very big atom. There are lots of atoms that come after neon in the periodic table. So neon has 10 electrons, but what about if you add just 1 more? Sodium is that 1 more. Sodium has 11 electrons. So just like we filled them in for neon, we put the first 2 on the first shell, because that's how many it can fit. 2 down. We can then fit 8 on the second shell right here, 10 down, but we still have 1 more electron to go. So that final last electron will go on the third electron shell. So now we have 1, 2, 3 electron shells. So the third electron shell is basically very similar to the second shell. It can also fit 8 electrons on it. So the first shell is only 2, but then the second shell is 8, and the third shell is 8. So sodium has 11 electrons, 2 on the first shell, 8 on the second shell, and then the last one on the third shell. If we look at a little bit bigger atom, something like silicon, silicon has 14 electrons total. Its atomic number is 14, so it has 14 protons and 14 electrons. So if we want to figure out how many electrons go on each shell, we start off with the first shell, that gets 1, 2. We go to the second shell, that gets 8. Now we've put down 10. But we have 4 electrons left over. So we'll put those last 4 on the third shell, right here. So 2 on the first shell, 8 on the second shell. Then the second shell gets full, so we put those last 4 on the third shell. So if we want to look at an atom that has all 3 electron shells full, we can look at something like argon. Argon has 18 electrons. So it has 2 on the first shell. It then has 8 on the second shell, but those are only 10 electrons down, so now I have 8 left over, and the final 8 electrons go on the third shell. So argon has 2, 8, and 8, which gives us 18 total electrons across the 3 shell. So argon has a full first shell, a full second shell, and a full third shell. So each electron shell can fit a certain number of atoms. And if you know how many electrons that an atom has, you can figure out how they're distributed across the shells by starting on that first shell, filling it in with 2. If you still have some left over, move up to the second shell, fill that one in. If you fill that second shell up with 8 electrons, and you still have some left over, you'll move on to the third shell. So there are more than 3 electron shells. It goes and gets bigger and bigger and bigger. But we're just going to worry about the first 3 in this class. We're just going to kind of focus on these little bit smaller atoms and not worry about the bigger ones. So first shell is 2 electrons. Second shell is 8 electrons. And the third shell is also 8 electrons. All right, so we're going to do a whole bunch more examples of these, including I'm going to have you guys help me out with a couple examples. But does anybody have any questions so far? Any initial thing about the electron shells that you're a little confused by?
So no more than 8 electrons after the first shell, right?
Mm-hmm. Yeah. So the second
yeah.
shell and the third shell get a maximum of 8 on them.
No more than 8, okay.
Mm-hmm. Exactly. Good question. So like I said, let's look at a couple more examples. So nitrogen is a pretty small atom. It's pretty close in size to carbon that we're looking at earlier. And nitrogen has only 7 electrons. So here's our little nitrogen nucleus. And then 7 electrons means on the first shell, we put down 1 electron, 2 electrons. And then on the second shell, we have 5 electrons left over. And so we can fit all 5 of those on the second shell. So nitrogen has 2 on the first shell and 5 on the second shell to give us a total of 7 electrons. Neon is an example that we looked at already with having a full first shell of 2 and second shell of 8 to give us 10 electrons total. And then aluminum is also another good example. Aluminum has 13 electrons. So we start figuring it out by filling in the first shell, 1, 2. All right, but we still got 11 electrons left over. We then go to the second shell and start filling it in. 1, 2, 3, 4, 5, 6, 7, 8. Well, now we've filled in 10 electrons on those first 2 shells, but we still have 3 more electrons that we haven't put down yet. So those 3 will go on the third shell of aluminum. So you always, if you're not sure exactly about where the electrons are going to go, you always start by filling in the first shell and then moving out to the second shell if you need to. And then after this one is full, moving out to the third shell if you still have some electrons left over. All right, so just to get a little bit more practice with that, I'm I'm gonna bring up a little whiteboard here. Let's see, I think it's under here. It is. Hold on, let me get this on the screen here. All right, let's see here. And then present, and share window, and the whiteboard window. All right, so if you've never seen it before, this is a Jamboard. It's essentially like an online whiteboard. And so let's do a couple examples of this together as a class. So I'm going to kind of pick out an element at random that we haven't talked about yet. Let's see here. Boron. Boron's pretty good. So boron is an atom that has a chemical symbol of and an atomic number of 5 and an atomic mass of about 11. So the first thing that we got to figure out is how many electrons are in boron.
5.
5, precisely. So remember, the atomic number tells us how many protons that we have, but also how many electrons that we have. So boron has 5 electrons. So I have 5 electrons. In science, a lot of times people like to write electron as like a little E minus because it means like a little negative electron. So I got 5 electrons. So if we have our boron nucleus, let's make 1, 2, 3 shells. I know they're not great circles, but circles are hard to do on a computer screen, as it turns out. So here we've got boron, and we've got some electron shells around it. So let's start filling these in. So how many electrons are going to go on the first shell of boron right here?
2 in the top and under
2.
1. 2.
So we can do like 1, 2 electrons on the first shell. So now the first shell is full. Do we still have more electrons to go?
Yes, 3 more.
3 more.
Mm-hmm. Yeah, so we put down 2, so now we've got 3 more to go. So where are those 3 more electrons going to go?
Second shell.
Yeah, on second line.
Second shell. Bingo. 1, 2, 3. So we've got 2 electrons on the first shell and 3 electrons on the second shell. So now we put down all 5 electrons for boron. So does boron have any electrons on the third shell out here?
No.
No.
No, exactly. We already put down all the electrons we're going to have. So boron has an empty third shell. It doesn't have anything on its third shell. So excellent job. You figured out starting off with that first shell and then putting the remainder on the second shell. So boron was a pretty simple, pretty basic example. But let's cross it out and maybe do something a little bit bigger. Probably could have just made a whole new blank slide, but oh well. Now we're too committed to the erasing. All right, we'll leave it a little bit messy. That's okay. We'll survive. Now the question is, where is the mouse? There it is. All right, let's see. What is a good one that we could pick? Ooh, chlorine. Chlorine is a great example. So chlorine has an atomic number of 17 and an atomic weight of about 35. So 17 and 35. We'll make our little chlorine 1, 2, 3 rings out here. All right. So first up, we got to figure out how many electrons are in chlorine.
17.
17, exactly. So atomic number is 17, which means that we have 17 protons and 17 electrons. Okay, so chlorine has 17 electrons. So where are the first electrons gonna go?
Going to the first, so 17.
And how many on the first shell?
2.
2, precisely. First shell can only fit 2. So we've got 1, 2. Actually, hold on, wait. I could do like this for electron. Ooh, that'll be fun. Okay. So we're gonna switch it up a little bit, make things a little bit more colorful. So we've got 1 and 2 electrons on the first shell of chlorine. So now we don't have 17 electrons to go anymore. Now we've only got
15.
15 electrons to go. So after we're done with the first shell, we move on to the second shell. So how many electrons can fit on chlorine's second shell?
8.
8, precisely. We got 1, 2, 3, 4, 5, 6, 7, and 8 electrons on chlorine's second shell. So 8 is the maximum. We can't fit any more electrons on the second shell here. It is all full. But we're not done yet, right? We put down 8 of our remaining 15 electrons. So now we still have 7 electrons to go. So can we fit 7 electrons on the third shell of chlorine around here?
Yes, we can.
3 is right. We sure can. 1, 2, 3, 4, 5, 6, 7. So now we have finally run out of electrons, right? We put 2 on the first shell. We still had some more, so we put 8 on the second shell. That one was full, so we put our final 7 around the third shell. So we have a total of 2 plus 8 is 10, plus 7 is 17 electrons. 2 on the first shell, 8 on the second shell, and 7 on that third shell. All right, so again, pretty straightforward. Start off by filling in the first shell. If you have any electrons left over, fill those in on the second shell. If you fill in 8 on the second shell and still have some left over, you fill in the remainder on the third shell.
If
Alright.
we have 24 electron, what we gonna do? We make one more
So
cell.
with 24 electrons, you'd start going out to like the 4th or 5th shells. So there are more electrons that can fit more electrons, but we're not going to focus on those ones in this class.
Okay.
So in this class, kind of first just starting off talking about it, we're only going to look at these first 3 shells. So if I ever ask you a question related to electron shells, it's never going to be with an electron or with an atom that would have more than 3 shells. But the basic process is the same. I think most electron shells can fit 8 electrons on them. So you'd fill in those electrons, and then if you still needed more, you'd go up to the 5th cell or the 6th shell or whatever it might be. So, but for this class, for IPC, we're just going to worry about first cell, second shell, third shell. All right, good question, though. I like that you're thinking ahead already. So I know that Dewey and Araceli have this down pretty well. Does everybody else feel pretty comfortable with it? Everybody else kind of understand how we got the electrons, where we got them?
Yeah,
Yes.
I'm good with it.
Can we do one more?
Sure thing. Ooh, there we go. Clear frame. That probably would have been easier the first time. All right, let's see. Let's kind of look for an in-between one of the ones that we were just doing. Let's see, fluorine. Fluorine looks like a good one. All right, so fluorine, on the smaller size of atoms, fluorine has an atomic number of 9 and an atomic weight of approximately 19. We've got our little fluorine nucleus, and then we've got this shell, and then this shell, and then ooh, this is the best one. That almost looks like circles so far. All right, so the first thing that we're going to do is figure out how many electrons do we have in an atom of fluorine.
Nine.
9, exactly. Atomic number of 9 means 9 protons and 9 electrons. So we've got 9 electrons to start off with. So as always, we start on the first shell. So how many electrons can we fit on the first shell of fluorine?
2.
2, precisely. 1, 2. All right, so we've used up 2 of these 9 electrons. So how many electrons do we have still to go?
7.
Exactly. So now that we put down the 9, let's put down the rest of them. And remember, we can only fit 8 on the second shell. So you can do 1, 2, 3, 4, 5, 6, 7, and that's it. we had 7 more electrons, and we put 7 down on the second shell. So now we are out of electrons. We've assigned them all to the correct shells. So does fluorine have any electrons on its third shell?
No.
That is correct. So first shell gets 2, second shell gets 7. So that gives us 9 electrons total. So we don't even have to go up to the third shell for fluorine. We're able to fill in just the first and second shells. Since we didn't have more than 8 to go, we didn't have to kind of extend out to that next shell. So 2 electrons on the first shell and 7 electrons on the second shell give us a total of 9 electrons for fluorine. So we started off on that first shell with 2. We then had 7 left over, and those 7 were able to all fit nicely on the second shell. No need to go out to the third one. All right, that help a little bit, Brandy? Any other questions or things that you want to look at? All right, does not sound like it. So that is how our electron shells work. We figure out how many electrons does this atom have, and from there we can start placing atoms on the first shell, and then if that's full, on the second shell, and then if that gets full, with 8 on the third shell. All right, there we go. So 2, 8, 8. That's kind of the big thing to remember about our first 3 electron shells. First shell fits 2, second shell fits 8, third shell fits 8. All right, so moving on from there, something that we're going to touch on a little bit today, but we'll actually be going over in a little bit more detail with some of the notes next week, is this kind of idea of reactivity, or how atoms interact with other atoms. And one of those things that scientists first found when they were studying atoms is that atoms really want their electron shells to be full. What that means is whatever their outermost shell is, if that's their second shell or their third shell, or even their first shell, if they're a really small atom like hydrogen and helium, atoms really, really want that outer shell to have a nice full set of 8 electrons in it. And so a lot of times the interactions that atoms have between each other is a result of them trying to set up a situation where their outer shell has a full 8 electrons in it. So some kind of basic examples of ways that they do this that we're going to be talking about a lot next week when we talk about making bonds between atoms, is that sometimes atoms will share their electrons with each other. So for example, the blue hydrogen is sharing its electron, and the green hydrogen is sharing its electron. So now when they both share these together, both of these atoms feel like they have a full first shell. They both feel like they have 2 electrons on that first shell, because they're sharing their one single electron with each other. Another type of thing that atoms will do to try and make their first shell do full is they'll give away some of their electrons to other atoms. So like sodium, we talked about earlier, sodium's in kind of an awkward position because he has 11 electrons, which means that he has 2 on the first shell, 8 on the second shell, and he's only got 1 little electron on the third shell. So there was some way that sodium could give away that 1 little electron, then he'd have a nice, full, happy second shell. Other atoms, like chlorine, are very close to getting that full outer shell. If you remember that one of the examples that we did together was chlorine, and chlorine has 7 electrons on its third shell. So if chlorine could just get 1 more electron added to it, then it would have a full third shell. So when these types of atoms come together, they interact with each other, and usually what happens is that the sodium atom will give up its electron to the chlorine atom. That way, the sodium feels like it has a full second shell, and the chlorine gets to feel like it has a full third shell, all because that 1 little electron transferred from the outer shell of the sodium atom into the outer shell of the chlorine atom. So whenever you see chemical reactions happening, this is sometimes one of the ways that those reactions occur, is by this transfer of electrons. Like I said, we'll go into these two kind of situations a lot more in some of our notes next week. But how easily atoms share or give away or take electrons is called their reactivity. So we talked about reactivity a little bit when we were talking about chemical properties. I mentioned that how reactive an atom or a chemical is one of its chemical properties. And so an atom that's more reactive means that it is more likely to go through a chemical reaction with other atoms and elements, usually in a very kind of rapid and sometimes explosive way. So the easier and speedier that atoms go into reactions with each other is the more reactive that they are. So atoms like sodium and chlorine are very, very reactive because their outer shell, for sodium, it's very empty, but for chlorine, it's almost full. So the closer they are to having those 8 outer electrons on their shells, the more reactive they are. Like the more they really, really, really want to have that outer 8 shell. So sodium really, really wants to give away that 1 electron hanging out on its third shell. And chlorine really, really wants to take an electron from another atom so it can have a full set of 8 on its third shell. So the closer that you are to having a full or empty outer shell, the more reactive that you are as a chemical, as an atom. And so the faster and easier you will react with other atoms in order to get your electrons set up the way that you like. So pure sodium is so reactive that it has to be kept in special like airtight containers, because if you let it interact with the moisture and the air, it'll explosively react. So it'll go through this explosive reaction just by coming into contact with the air because it is so reactive. It is so ready to give away that electron that it'll very, very quickly and very explosively go through those types of reactions. So like I said, I didn't want to dwell on this kind of part of it too much because we are going to talk about it a little bit more next week. And that's when you'll have a couple assignments that deal with some of this stuff. So the final thing that I wanted to talk about with you guys today is sort of the 3 major groups of atoms on the periodic table. So if you remember, yesterday or on Tuesday at the beginning of the day, I showed you a picture of the periodic table and was like, wow, look at all these boxes, look at all these numbers and letters and stuff. that are in here. So like here's boron that we were just working with a little bit ago. Here's fluorine, here's chlorine down here. And so you may have seen that it was colored different colors and not really thought anything of it. But there actually is a reason why this particular periodic table is set up with these different colors. And that's because these colors represent the three major types of atoms, the three kind of categories that we can put elements into. Either they are metals, which make up most of the periodic table, especially in kind of the left and middle section right here. There are nonmetals, which make up basically the far right-hand side of the periodic table. In this case, they're colored green, except for little hydrogen way out here by himself. He's so small. And then the metalloids are sort of like this weird in-between group that are kind of like metals and kind of like nonmetals. And so what I'm going to go over today and what your Friday homework is about is the differences between metals, metalloids, and nonmetals. So we'll start off talking about metals. And so when you think about metals, I want you to think the exact picture that comes to your mind, which is probably something similar to like aluminum foil. Right? Aluminum is a great example of a metal. Aluminum is right here on the periodic table. And it's something that I'm assuming pretty much everybody has some aluminum foil in your kitchen. So most metals have similar traits to aluminum foil. They tend to be shiny, so they tend to be kind of reflective and sparkly a little bit. They are usually solids at room temperature. So like aluminum foil is a solid, right? It has a set shape and a set form, a set size, stuff like that. The reason why aluminum foil is so flat and thin is because most metals are malleable, which means that you can squish and compress them down into like thin surfaces. So like other things might just kind of break and shatter. Like think about if you tried to take glass and squish it down, it would just break on you. But metals it's easier for them to get nice and squished and flat. Metals are also ductile, which is basically just a fancy science word, meaning that you can twist them up into like a wire. So if you've ever looked at the wiring inside of your house, I had to do some of this recently. My dad and I put some new ceiling fans in my house. And so we had to unwire the lights that were there before and rewire the ceiling fans. They're covered by these like plastic covers to help keep them insulated and safe. But the actual wire part are these thin strands of twisted up metal. So metals, you're able to thin them out and twist them up and turn them into wires. And that's what ductile means. The reason why metals are used in wires is because metals are very, very conductive. And what that means is that they can move heat and electricity across them very easily. So this is why most of your cooking ware in your house, most of your pots and pans are made out of metal. Right, I'm guessing that they're not made out of like wood or rock or glass or something like that. And that's because metals can move heat very, very efficiently around the pan. So even though if you're like cooking on a gas stove, the heat technically is only coming up right in the middle of the pan. But because the pan is metal, the whole pan gets hot, right? If you have like a metal handle attached to it and you grab that metal handle, you're going to burn your hand because even though the handle isn't on top of the flame, it's still hot because it's metal touching metal. So heat moves very easily through metals. That's why you usually stir things with like a plastic or wooden spoon because you can stick the wooden spoon into the boiling pasta water for a couple minutes and the end of the spoon isn't going to get hot. It's still going to be just fine because it is not a good conductor, but metals are. Same thing with electricity. It's very easy for electricity to pass from one side of metal to another. That's why if you ever stick like the points on a fork into the outlet, you're going to have a real bad time because the metal of your fork conducts the electricity through the outlet, and it's going to conduct it right into your body. And that's not good. Do not do that. That's why, like, I have a 1.5-year-old, and we have to put the little covers over all of the outlets because we don't want her accidentally sticking something in there. If she managed to get like a plastic, like one of her like rubber spoons or plastic spoons and stuck it in there, nothing would happen because rubber and plastic are very bad conductors. They don't move that electricity very well. So, but the metal is the one that does. So just like aluminum foil, shiny, squishable, solid, you can twist it up into a wire if you want to, and it's going to heat up really quickly, and it can conduct electricity very easily. So those are all the typical properties of metal. So if you ever see a question asking you about a property of metal, picture in your head some aluminum foil and how that would be like. The opposite of metals, essentially, literally on the other end of the table, are the non-metals. So non-metals have a lot of the opposite properties of metals. So non-metals, for the most part, they're not solid at room temperature, they're gas. There's some of them that can be solid, but a lot of them, things like oxygen, nitrogen, helium, hydrogen, these are all gases at room temperature. You'd have to get them super, super duper cold to turn them into liquids or solids. Non-metals are not shiny, right? A, it's hard to be shiny when you're a gas. And B, even when you're not a gas, things like sulfur are still very rock-like. And so they're not like shiny, sparkly like crystals. They're kind of rock and mineral-y. Non-metals, bad conductors, right? Rubber is made out of a lot of carbon, and carbon is a non-metal. So carbon does not conduct things very well. Same with wood. Wood is a lot of carbon. And then when they are solids, they are very brittle. So they break and shatter apart fairly easily. So they don't get nice and squished down or nice and wiry like metals. Instead, they just shatter into a million pieces if you try and do any of that stuff. So when you think about non-metals, I want you to kind of picture like basically like a rock. A rock is a great example of a non-metal. It's not shiny. It doesn't really get hot if you heat it up or conduct electricity. The one downside of imagining a rock is that a rock is not gas, but a lot of non-metals are gas. So think like the oxygen that you breathe is a non-metal. It's floating around in the atmosphere. And then the solids are very brittle. If you try to flatten around a rock, it's just going to break and shatter in your hands. So again, metals, non-metals, basically the exact opposite properties. That's why they're on the opposite ends of the periodic table. The kind of weird mixture in the middle is the metalloids. So metalloids, there's not very many of them, and you can see on the periodic table, they are literally in between the metals and the non-metals. So they have some metal properties and some non-metal properties. So metalloids are usually solid at room temperature, like metals. However, those solids tend to be very brittle and hard. So it's very easy for those to break and shatter like nonmetals. Metalloids are kind of good conductors. They're semiconductors. So what I mean by that is that metals will always conduct electricity and heat all day, no matter how they are set up. Metalloids sometimes conduct electricity, but only under certain conditions. So they can be very, very, very good at conducting electricity, but it has to be under a specific set of circumstances. So a lot of computer chips are semiconductors because they're extremely good at moving those electrical signals in your computer around very well. But when scientists are designing semiconductors, they have to make sure that they fall into those certain categories. Otherwise, they're not going to work. So silicon is a very common example of a metalloid. There's a lot of silicon in semiconductors and other computer parts. That's why the area of California where like Google and Facebook and Twitter are located is called Silicon Valley, because a lot of computer related stuff kind of came out of that area. But it also is pretty common in things like glass and sand, essentially. So metalloids are solid, but they're kind of breakable and they can conduct electricity, but kind of sort of only sometimes. It's not as well as metals in any situation. They have to be put under very specific sets of conditions in order to have that semiconducting going on for them. So like I said, these guys are kind of right in the middle of the metals and the nonmetals. So in general, kind of like if we combine some of the last stuff that we were talking about in terms of reactivity. So with our metals, our very reactive metals tend to be more towards the left side. So like we were talking about sodium earlier, and sodium is a very, very, very reactive metal. And then as you get closer to the middle of the periodic table, these guys are not as reactive. So like this guy right here is silver, this one is gold, this one is aluminum. Those guys are not particularly reactive metals, right? That's why they make good everyday wear or jewelry, because they don't react with other stuff in the environment. Nonmetals are kind of the opposite. Nonmetals, the ones closer to the middle of the table, are lower reactivity. And then as you move towards the right-hand side, you get more and more reactive nonmetals. So things like chlorine, we talked about earlier, is pretty reactive. And same thing with like fluorine and iodine. These are all very, very reactive nonmetals. The exception to this is this final column of gases right here, this final column of nonmetals. Things like helium, krypton, neon, xenon. These guys are extremely low reactivity. The reason for that is that all of these guys have a full outer shell of electrons. So they're called the noble gases because they do not react with basically anything else on the periodic table. They just like to keep to themselves and not mix with the other stuff. And so if you remember, helium has 2 electrons on its first shell. Neon has 8 electrons on its second shell. Argon has 8 electrons on its third shell, and so on and so forth as you move down the group right here. And so these guys have the full outer shell already. Remember earlier I was talking about how atoms are more reactive the closer that they are to that full shell. They want that full outer shell. These guys got it. These guys were born with it, basically. They have a full outer shell of electrons. So they don't need to be reacting with all those other elements that are over there in the table. They are just fine and dandy, being fat and happy and sticking to themselves. So that's why they're called the noble gases. It's like they don't want to mix with all the peasants and the rest of the periodic table. They want to stay pure and pure to themselves. All right, but that is our nonmetals over here, our brittle gases, our shiny and squishable and conductive metals, and then our kind of weird mix of both in the metalloids right here. All right, so does anybody have any metal, non-metal, metalloid, or reactivity questions?
No?
No questions.
Righty. So for today's assignment is pretty straightforward. So the first one, today's Thursday assignment, deals with those electron shells again. This time it's specifically for the element oxygen. And so you have a little periodic table box of oxygen right here. The first thing that I want you to do is kind of remember what we talked about on Tuesday. And so the first three questions are protons, neutrons, and electrons. How many of them are in oxygen? But then the next three questions are about the electron shells. So I want you to tell me how many electrons go on the first shell of oxygen, how many, if any, go on the second shell, and then finally, if you still have more, how many go on the third shell? So if there aren't any that need to go on the third shell, you can just write like none or zero. But if they are, you would answer that in this last question down here. So hopefully that work that we were doing earlier, kind of going through some of those examples, has got you pretty well equipped for today's assignment. And then tomorrow's assignment, I'll give you guys a little sneak peek since you're on the call with me here today. Has to do with those metals, metalloids, and nonmetals that we were just talking about, where I have all of the different categories, all of kind of the different properties of metals, metalloids, and nonmetals over here on the left. And then for each one of these, I want you to check off, does this best describe a metal, a metalloid, a nonmetal, or some combination, right? So some of these might describe only one of these three types, but some of them might be two. So there could be more than one substance that matches the description. And so if you think that there are multiple things that are brittle when they are solid, you would put the check boxes inside whichever one, however many of these you think fit that description. So I will go ahead and tell you guys that none of them are all three. So each description fits either one or two of the type of substance. And so which one of these are shiny? Which ones are gases? Which ones break easily when they're solid? Which ones are solids? Which ones are known to be semiconductors? Which ones tend to be dull? Which ones are squishable and pullable? Which ones are bad conductors? And which ones easily transfer heat? So you just go through and check off each one that fits the description. All right, so today's assignment is calculating the particles and the electron shells for oxygen. And then tomorrow's assignment is filling out that little checkbox for the metals, metalloids, and nonmetals. Anybody have any questions about any of the homework or anything that we talked about here today?
No, I don't.
All right, thanks, Dewey.
We done today?